Welcome to Final Element Methods Abaqus tutorials. I'm Leonardo Araque, a PhD student at UCLA, and I will guide you through this tutorial. The purpose of this tutorial is to obtain the dynamic modes for an aircraft wing. The aircraft wing span is 4,000 millimeters and is made of aluminum, which density, Young's modulus, and Poisson ratio are presented in the slides. The components of the aircraft wing are the cover, ribs, spars, and stringers. Let's start by modeling this structure in Abaqus. From the module part, we create the first part, which corresponds to the cover. This is a 3D deformable shell type extrusion with approximate size of 1,000. From the sketch library, we select the sketch number 1. 4 sketches have been already created for you. We click Done. One more time to define the depth for the extrusion. The depth for the extrusion is 4,000 millimeters. Once the cover has been created, we can proceed to create the second part, which corresponds to the ribs. This time, we create a 3D deformable solid, and we're going to use the type extrusion. We can keep the same approximate size. From the sketch library, we select the sketch number 3, and we proceed as we did before. This time, the depth for the extrusion is 20 millimeters. Once the rib has been created, we can proceed to create the third part. The third part corresponds to the spar. The spar is also a 3D deformable solid extrusion, and we use approximate size of 1,000 millimeters. From the sketch library, we select the sketch number 4. And we proceed to erase the sketches corresponding to the stringers, leaving behind only the sketch corresponding for this part. We click Done one more time, and now we can define the depth for the extrusion, which is 4,000 millimeters. We need to create one more part. This part, this time, for the stringers. This is a 3D deformable solid. We use the type extrusion. We keep the same approximate size. And from the sketch library, we select a sketch number 4, and this time we erased the component or the sketch corresponding to the spar. Click Done, and define 4,000 millimeters as the depth for extrusion. Now we can get back to the ribs. Since this is a solid, we need to create a shell from the solid. So we can go to the definition in the following window. In the module part, we select Create Shell from Solid. We select the entire part. And then we can proceed to remove some faces. We remove the front faces, as well this other two. I need to unselect again. Once this faces has been selected, we can remove it. We still need to remove these faces related with the stringers and the spar. So we can continue. We select all the corresponding faces. Okay, not that one. Similar to this, we repeat for the others. Once all the faces corresponding to the stringers have been removed, as you can see, and as an example, we have this on the top. And we remember what we did before at the bottom. Now we can proceed to remove some faces located in the rib where the spar is supported. Same procedure for the bottom. All right. Now we can repeat a similar procedure for the spar. So the first step is to create a shell from the solid. So remember, go to create shell from solid, select the part, And once this is done, we can go and remove the faces. All right. So all internal faces are removed. For the stringers, we first convert shell from solid, and then for each of them, we remove all the internal faces. Leaving only the external face. If we repeat this procedure for the remaining stringers, we will obtain the following. Once we complete removing the faces on this side of the stringers, we need to go to the back side to remove some remaining surfaces like this one. Don't forget to do this. If you continue with all of them, now from this view, you can see that the faces has been removed. And leaving only the external surfaces. Once this step is complete, we can go to the module property and create a material. This is aluminum. The density, according to the information provided in the slide, is 2,700 e to the minus 12. This is tons per cubic millimeter. Now the junction modules in megapascals or newtons per square millimeter are 70,000 and the Poisson ratio 0.3. All right. This time we're gonna move to the module assembly to create the instances. To create the instances, we select all the parts and we create a dependent instance. Now, we're going to create a linear pattern to model the ribs along the span. So first, go to create an instance, select ribs, let's do it this way. Replace selected, select instances from this menu, select the rib, click done. So in this way, we can have only the rib. Now, go to linear pattern, select the part or the instance, and modify the linear pattern in the following way. The offset between each of the instances is 250 millimeters. And the direction is along the positive z-axis. All right, when this has been done, we need to modify the depth of the extrusion for the remaining parts, because this linear pattern has extended the span from 4,000 millimeters to 4.02 4,020 millimeters. So we need to modify this. So go in the tree, go to parts, select cover, expand pitches, and double click in shell extraction. And input the new dimension, 4.02 e to the 3. If you apply, you can see how the part is extended in the Z direction. Now repeat this procedure for the spars as well. And the stringers. Okay, once the instances has been created, we can go back to the module properties and create a section. So the first section will correspond to the cover. We select shell homogeneous. Oh, let me do the following. Oh no, that's okay. Shell homogeneous. And the thickness, and we define the thickness for this section, 15 millimeters. Let's define the other sections. The section corresponding to the ribs will be a shell homogeneous as well. And this time, the thickness is 2.5 millimeters. The next section will be defined for this part. It is also shell homogeneous. And the thickness for this is 3.800451. I need to create another section for the lateral component, horizontal component for the spar. So let's do the following. Let's redefine in part the name for this. Let's add a V for vertical. And let's create another section, which is part H. Continue. The thickness for this section is 3.97 38 21 millimeters. So the question is, where are these dimensions coming from? So if we go to the rib and we measure the gap between these two faces, we can find that the distance in the horizontal direction in the x direction is 3.00451, right? And if we repeat the same procedure with this dimension, we can see the thickness corresponds to the distance between these 2 points. So for we're going to repeat a similar procedure for all the stringers, so they can fit the corresponding spot in the ribs once we get to the part of the assembly. So let's get back the module. Let's get back to create the other sections, and then we're going to assign them to the corresponding parts. So now we go to the stringers again. Let's create for the stringer on the left. And let's do the vertical first. Same definition, shell homogeneous. Continue. The thickness is 1.02445 millimeters. Let's create one more. Left horizontal. The thickness is 976.209 e to the minus 3. We need to create some more sections. Now this is for the right. Vertical first. .13, 81, 68 millimeters. For the same group, now create the horizontal, or define the section for the horizontal with thickness 1.906459 millimeters. I'm just verifying that I'm not making mistakes. All right. We need to create 2 more sections. Now this is for the group of stringer in the middle. Let's do vertical first. 1.168, 2.259. And the last one. Horizontal. .190112. All right. When all the sections have been created, we can proceed to assign the section. So let's start with the cover. So assign section in the module property and select create set, toggle create set. And from the selection, select section cover. Since this is, we model this component as shell, we need to define the reference surface. So for this component, we're gonna use the top surface. as a reference. This is all related with the assembly procedure we're gonna do later. Okay, now we can move to the next one. Let's do the ribs. To assign the section to the ribs, we select the ribs. And from the section, from the edit section assignment, we select the section ribs and define I think I will need to split this section in two. So let me cancel this. And let's go back to create one more section. This section, ribs, let's say horizontal. Yeah. Category shell, homogeneous, continue, same thickness, 2.5 millimeters. And I'm going to rename these ribs with vertical. All right, good. So now we can assign the section. So we can select part. From the menu, we can select ribs vertical, and the definition is with respect to the bottom surface. Oh, 1 second. Okay. I only need to select the front surfaces. That's all what I need to select. Yep. Now we select ribs vertical, and we define the bottom surface as a reference. Okay, good. Now you can see that, well, now you can understand why I need to split this. I created another section because the next reference surface would be the top. So we create another, we assign the section now for the components, like the fins components, the lateral components of this part. All right, I think all the components were selected. This time we select ribs H and define as a reference surface the top surface. Let's do an instruction that there is not component or surface without section. So all the part turn green, so it means that we didn't leave any assigned section behind. All right, so now we can proceed with the next part, which is this part. For this part, we select this surface only, the front surface. We look for the corresponding section, spar vertical, and we define the reference surface as the top surface. Now we need to assign another section to these two fins or laterals. Look for the section spar H and select also the top surface. All right. Now the stringers. So this group was defined, will be assigned with the left. All right. This group middle and this group right. Okay. One more thing. From this view, those are V and these are H. Yes. Yes. Okay. So let's do assign the section. Let's do the verticals first. So section, stringer, left, V, and the corresponding surface is top surface. Give me 1 second. Right. I just verified that that was the correct orientation, so I can proceed now. So from this view, this group on the left will be assigned the sections to these verticals. Um, Stringers left verticals. And the reference surface is going to be the top surface. Okay. For the laterals, we'll be select stringer left horizontal. And the reference surface is top surface. All right. Now let's do the group in the middle. We select the verticals. And we look for the stringer middle vertical. Reference surface, top surface. Now the laterals. Stringer middle edge. Reference surface, top surface. Now we move to the group on the right. Let's do the verticals. Look for right V. Reference surface, top surface. And now look for, select the laterals and look for right edge. Reference surface, top surface. Okay. One, this has been done. Just let me verify the right vertical and horizontal. That's the vertical and this is the horizontal. Yes. All right. So the sections has been created. So the next step is go to the next step is the assembly. In the assembly, we need to look at the entire we need to look at the assembly. So I'm gonna replace all. Now we have all of them. And we can put the following. We look for, in this module, we look to merge the instances. We select merge cut instances, and in this dialog box, we're gonna select merging geometry. The selection, the operation is merge through the geometry. We keep this, we accept the option suppress for the original instances, and in geometry, we select retain. Continue. We select the instances, all of them, and we click done. So this is what happened. We go to the tree on the left-hand side, and we click on assembly. We expand assembly, and then instances. You can see that all the instances we created are suppressed now. And the active instance is the merging geometry. All right. So this is what this this operation has been done. All right. So the next step is to mesh. Or let's do first. Let's create a step to apply the load. Let's say this is static analysis, right? Let's name static and select static general. Accept the conditions. Click OK. And now let's go to load. And let's apply the boundary conditions. So for the boundary condition, for the initial boundary condition, in the category mechanical, we select the first option, symmetry, antisymmetry, symmetry, antisymmetry, and completely constrained in castry. We look for the root. All right. And we select only these two surfaces. And we completely constrain them. All right. Next step, we're going to apply some displacement on the opposite end. So let's call this displacement up. select the step static, and make the selection a displacement and rotation. So we can define the displacements we want to apply. So let's look for the opposite face. Good. Let's select the faces. We need also to select these lines corresponding to this part. So I'm going to select first the lines corresponding to this part. So you can see it. And now I'm going to proceed to select again the surfaces. All right. So when this is done, again, I need to create a boundary condition, the displacement. So apply step static, category mechanical, select displacement and rotation, continue. Since the surfaces have been already selected, we select displacement 1, displacement in the 2 direction. Let's apply minus 10 millimeters and apply 10 millimeters positive in the 2 direction. Okay. So now we can see at the root the essential boundary condition, completing cluster, and the opposite end, the applied displacements. All right. So next step, we're gonna mesh. To mesh, we're gonna toggle to part and select the merging geometry. We need to see the part. Let's accept this global size. Let's mesh the part. Let's look for the assigned element type. Let's select the entire part, and from the element library, the standard element library, we should select show, but it's okay by default, or Abaqus selected for us, and I'm gonna stay with this selection. And the geometric interpolation is linear, so it's okay. We're gonna keep this selection. We're gonna accept this selection. So finally, we're using a 4-node element, shell element. Let's go to the mesh controls. I'm gonna accept these conditions. So we can see from this view the mesh we have created. All right. So next step is to create a job. Step one, let's say displacement, job displacement. Once we create a job, we can submit it. Once the job has been completed successfully, we can look at the results in the module visualization. Looking at the result, as the previous results were not what I was expecting to see, so I went back to the definition of my boundary conditions, and I noticed that one of the surfaces I was supposed to select was not selected. So I corrected. I corrected this wrong selection, and I ran it again, and this is the final result. So this is the what misses stress for the wing and under the loading condition we specify. Now I'm going to proceed to remove this step, loading step, and to extract, to obtain the modes of vibration. All right. Now I'm going to to duplicate this model so I can have the two versions of this final element analysis. One with applied loading, the displacements -10 and 10 millimeters, and the model to extract the DNA of the dynamic analysis. So let's rename this as model 2. I'm gonna contract this and expand model 2. And all what I need to do is go to the definition of the step. I'm gonna suppress this step and create a new one. This step will be the, let's call modes. Vibration. In the procedure type, select linear perturbation and frequency. We keep the pre-selected eigensolver, and we only need to specify the number of modes. we are interested. Let's select 5. All right. So the next step is just go, close this window. If we go to load and we look for the boundary condition manager, the apply displacement has been suppressed. So all we need to do is to create another job. And this time, I'm going to call this job dynamic. Let's call wing dynamic. And run the model. Once the job has been submitted and completed successfully, we have the results. So the IM values, which are the frequencies, can be seen in this window, and we can go over all the 5 modes we already pre-selected. With these results, I finish this tutorial.